All right, page 3 of your chapter 9 study guide. Number 14 asks you to graph each number in the complex plane, then find its absolute value. Two very important things to remember. Thing number one is that if you're not in the habit of labeling your axes, most of the time it's okay. But in the complex plane, it is very important that you actually label the horizontal axis as the real axis and the vertical axis as your imaginary axis, which is I. Okay. Graphing the number is actually pretty simple. Your A is 5, and your B, the number in front of I, is just 1, or that could be your X and your Y. So graphing is really simple. That means the real component is 5. So along the real axis, you go 5, and then you go up 1. So this is where the second place where many people are going to make that mistake. When you graph the complex number, you actually need to connect the origin to that final coordinate point. Okay, this represents the entire number. The hypotenuse represents the entire number, not just the point floating in space. To find its absolute value, that's the distance away that its endpoint is, or the length of that whole hypotenuse, which could be found by doing the square root of a squared plus b squared. So it'll be 5 squared plus 1 squared, which will be the square root of 26. 26 cannot be broken down any further, so we will leave it as is. Part B is very similar. A is going to be the first number, which is -4. B will be the coefficient to the imaginary component, which will be -4. Again, we'll label our axis as R and our vertical axis as I. And then when we graph these points, we'll go 4 to the left and then 4 down. And be sure to connect the origin to that point. So that represents the entire complex number. To find its absolute value, we will take the square root of -4 squared plus -4 squared, which is going to equal the square root of 16 plus 16, which is 32, right? Which this will end up being, breaking up the square root of 32 is the same thing as the square root of 16 times the square root of 2, which this will reduce to be 4 square roots of 2. Okay. Number 15, it says express each complex number in polar form. Leave all r as simplified radicals and all angles in radian form. For A, theta should be rounded to the nearest hundredth. For B, it should be exact. In case you didn't pay attention in class, I changed these. I want B to be rounded to the nearest hundredth, and I want A to have an exact value for theta. So we're going to change those. All the other directions, though, are still the same. So the first thing that we need to do, if you're going to express this number in polar form, is you need to figure out what are r and theta. So if we have A and B here, then r is going to equal the square root of A is -1 squared, plus B is the coefficient of I, so it's just going to be +1 squared. So it'll be 1 plus 1, which will be the square root of 2. So r is the square root of 2. Theta is going to equal, using our equations way back on page 1, number 7, tangent inverse of y over x. So y is, or in this case b, will be 1 over. The x value, or the a value, is -1. Now, because my x value is negative, then I also have to add pi, right? Because x is less than 0. Now, I want this theta to be exact, which means when you simplify, this would be tangent inverse of -1 plus theta. So, plus pi. So if I want this to be an exact value, when you take the tangent inverse of -1, I want you to look at your unit circle. And I want you to first find where is the tangent value at +1. So in other words, what angle theta has a slope of +1? Well, that obviously is going to be pi over 4. So if I want the tangent of -1, where's the value, or where's the slope -1, that's going to be at the value -pi/4. Now, technically, you could choose -pi/4 is the same thing as 7pi/4, or that's also the same thing as 3pi/4. But we want what's called a principal value, so we want the value that's closest to 0, if that makes sense. That's closest to the 0 or 2 pi on the unit circle. So the best way to do it is take the inverse tangent of the positive slope and then just make it negative. This means we go, instead of going a positive pi/4 on the unit circle to get a slope of 1, we go downward -pi/4. And then we're going to add pi. Well, when you add these two, if you kind of ignore pi and you just treat the other parts as fractions, this will be 4/4. So then we get -1/4 plus 4/4 will be a positive 3/4. So this would be 3pi/4. So you found r and you found theta. Well, using what we wrote on question 12, these are the rectangular forms and polar forms of complex numbers. We will write this in polar form, which will be the square root of 2 times the cosine of 3pi/4 plus I times the sine of 3pi/4. Okay, or if you write it in the abridged version, it would be square root of 2 CIS 3 square roots of, 3pi/4. That would be acceptable as well. Okay, sorry for the dogs going crazy. It just rained and there are a bunch of birds outside and they like to chase birds and they can't go outside because it's raining. So anyway, I apologize for any future barks you may hear. Copper, come here, Buggy. All right, part B, same idea. I want you to convert this into polar form. So the first thing we need to do is find r. R is going to equal the square root of -4 squared -4 squared plus 3 squared, which we get the square root of 16 plus 9, which is 25. So then r is equal to 5. So that was pretty easy. This time, theta is also going to be easy because for b, you can round it to the nearest hundredth. So theta is going to be tangent inverse of y over x. So it's going to be 3 over -4. Again, x is less than 0. So because x is less than 0, that means I also need to add pi. And since you can round to the nearest hundredth, you're going to plug this straight into your calculator as is. Again, making sure that you are in radian mode. Unless specified for degrees, the default is always radians. When you substitute this into the nearest hundredth, you're going to get that theta is about 2.50. So writing your answer in polar form would be 5 times the cosine of 2.50. Or you could just put 2.5. I'm not going to take off points for sig figs. Plus I times the sine of 2.50. Or if you write it abbreviated, it would be 5 CIS of 2.50. Either one of those answers would work. Okay, number 16 is kind of going the opposite direction. I give you the polar complex number, so notice these questions look like the answers from the question before, except I want you to go backwards. I want you to give me this number in rectangular form, the exact answer, and I want you to graph it as well. So in graphing it, remember, in order to graph a complex number, we just need r and theta. So this is the same thing as r is going to be 2, and then our angle is going to be 3pi/4. So if I want you to graph that point, you do the same thing that we were doing like on the first page. The angle will be 3pi/4, which is going to be, it's not on this exact graph, but again, the benefit of you having the unit circle, being able to fill out the unit circle that I give you, 3pi/4 will be this angle right here. So at that angle, if r is 2 from the pole, we are going to move toward that angle 2 rings away. Now, because it's a complex number, just like number 14, when you graph this, you actually want to connect the pole to that point. Okay, so there's the graph of it. When you convert this to rectangular form, I literally, in order for you to do that, essentially all you're doing is simplifying. So you're simplifying using the unit circle. So I just want to know what, are those numbers. So this will be 2 times, using my unit circle, the cosine of 3 pi over 4 is the x value at 3 pi over 4, which is going to be negative square root of 2 over 2, plus I times the sine of 3 pi over 4 is going to be positive square root of 2 over 2. And then you're going to distribute this 2 Sorry, had to fuss the dog. So you're going to distribute that 2 to both of these terms. 2 over 2 will cancel in each one of them. So then your final answer, and this is where you just have to pay very close attention to details. 2 over 2 will cancel. I'm just leaving us with negative square root of 2. Plus 2 over 2 cancels again, the square root of 2i. And even though I started in the front of this number, remember, if I ask you for your answer in rectangular form, we talked about this on the other page, has to be a plus bi. So you want a and b to be distinct from I. So you want this in this exact form, a plus whatever number b, and then I should be at the very, very end. Part B, let's graph it first. Negative 7 pi over 6. Well, notice that positive 7 pi over 6 is here. So that means we start at 0 and we go this whole distance to get there. So if I start at 0 and I go that 7 pi over 6 distance in the other direction, I'm going to end up at this point here at 5 pi over 6. That's the same thing as negative 7 pi over 6. So here's my angle. And R is 4, so I'm going to go 4 in the direction of that angle and then connect that point with the pole. So there's the complex number. To convert it to rectangular form, I'm just going to go ahead and simplify everything. So then I'm going to get 4 times the cosine of negative 7 pi over 6, which is the same thing as 5 pi over 6. The cosine, the x value at that point, using the unit circle, is negative square root of 3 over 2, plus I times the sine at that point, using the unit circle, that's the y coordinate at 5 pi over 6, which is 1/2. And then I'm going to distribute this 4 into both of those numbers. My first number is going to be negative. 4 divided by 2 is 2, and then I have the square root of 3, plus 4 times 1/2 is 2, and then I put I on the very end. So your final answer will be negative 2 square roots of 3 plus 2i. That's in the form a plus bi. Example C, graph this polar number first. So 4 pi over 3 will be this angle here. And then R is 3, so I want to go 3 in that direction, which will be here. So there's that complex number. And then to convert it to rectangular form, I'm going to use the unit circle to actually simplify these values. So then I get 3 times the cosine at 4 pi over 3, which is the x term, will be negative 1/2, plus I times the y coordinates at that angle is negative square root of 3 over 2. And then I'm going to distribute this 3 into both of those numbers. So my first number is going to be negative 3/2. And then 3 times I times negative square root of 3 over 2. Well, I know it's going to be negative. And then I'm going to put I at the very end. So my other numbers are just going to be 3 square roots of 3 over 2. And then I. And again, I want you to leave this written as 2 separate numbers, even though they both have a denominator of 2. And technically, I could write them together. If I want it to be in rectangular form, I need a distinct a plus bi. Okay, number 17. These are equations or formulas that you need to be able to generate and use. So the first one deals with, what if I am multiplying 2 polar complex numbers? The rule is we take our r's out front and multiply those, r1 times r2. times, we end up adding our thetas. So it'll be 2 times the cosine of, you're going to add theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. Okay, the second one is division. And when you divide, instead of, just kind of like we did in the last problem, you're still going to divide your r's out front, so r1 divided by r2. Your polar number is still going to have the same setup as the other one, which is cosine plus I sine, right? That's the general form of a polar number, except we are going to subtract our thetas. Okay, subtract the thetas, which is going to be the cosine of theta 1 minus theta 2 plus, you still add though, okay? We're not, you don't change both signs, you only subtract the thetas, but you still add I times the sine of theta 1 minus theta 2. So both of these are exactly the same, except in multiplication, you multiply the r's out front. In division, you divide the r's out front. In the multiplication, you add the two angles. In division, you subtract the two angles. And then this is the new one. This is the last part that we learned in this chapter. When you raise a complex polar number to a power, this is also called de Moivre's theorem. It's the same thing as the expression r to the n power times the cosine of n times theta plus I times the sine of n times theta. Okay, number 18 and 19. Okay, for 18 and 19, you're going to find the product or quotient, the power, that one's all going to be on the last page. Your answers are going to be exact and in rectangular form. So for number 18, notice I've got a multiplication problem going on here. So the first thing we're going to do is multiply the r's out front. That's going to be 1/2 times 6. Times, then we're going to, the format's going to be the same. It's going to be the cosine plus I sine, except we're going to be, because we're multiplying, we're going to add our thetas. So we're going to take pi over 3 from the first number plus 5 pi over 6. That's the second angle. So the cosine of this plus I times the sine of those same two numbers being added. Pi over 3 plus 5 pi over 6. This is a 3. Okay, and then we're just going to simplify. So 1/2 of 6 is 3 times the cosine of, actually, before I do that, let me not write everything out in the same step. I want to go off to the side and actually figure out what is pi over 3 plus 5 pi over 6 by hand. So if we treat these, if you kind of ignore the pi's for a second, and you just look at the fractions, 1/3 plus 5/6. If I multiply this 1/3 to get the common denominator, I'm going to multiply it by 2 over 2, which then gives me 2 pi over 6 plus 5 pi over 6. And then 2 pi plus 5 pi is 7 pi all over 6. So now when I can rewrite these added angles to be 7 pi over 6 instead. Okay, so now let me continue. 1/2 of 6 is 3 times the cosine of, I'm now going to have 7 pi over 6 plus I times the sine of 7 pi over 6. And you'll notice I'm kind of switching back and forth between brackets and parentheses. There's really no right or wrong answer in using those. Just many times if you're using multiple parentheses within a problem, you can use brackets in the very, very outside just to make it look a little bit different than a bunch of parentheses, but it doesn't matter. And then, so this is your answer in polar form. The only thing you got to do now is just convert it to rectangular. So you successfully used the equation, but now we want to simplify it. So if I'm going to simplify it, I'm going to use the unit circle to get an exact value. I'm going to locate the angle, 7 pi over 6, and I know the cosine is the x-coordinate at that angle. So the cosine of 7 pi over 6 using a unit circle will be negative square root of 3 over 2. Plus I times, again, I'm going to use the unit circle to get the y value, the sine, at 7 pi over 6, which is going to be -1/2. And then your goal is just to simplify this expression. You're going to distribute this 3 into both of those terms. So get -3 square roots of 3 over 2 once you distribute in the 3 to the first term. And then you get -3 halves, because that's 3 times -1/2, and then you tack on I at the very end. Number 19 is very similar, except this one is a division problem, so we're going to follow the division expansion here. We're going to divide our r's out front, so it's going to be 4 divided by 2 times the cosine of, the only thing you got to remember when you divide is that we're going to subtract the angles this time. So we're going to do 9 pi over 4 minus -pi over 2. Be careful, you're going to have a double negative here. Okay, plus I times the sine of 9 pi over 4 minus -pi over 2. So we're going to go off to the side and we're going to go ahead and actually do this subtraction. 9 pi over 4 minus -pi over 2. So first of all, we need to realize that this is going to change to 9 pi over 4 plus pi over 2. And then if I want to add these fractions, I need common denominator. So I'm going to multiply pi over 2 times 2 over 2. Me 9 pi over 4 plus 2 pi over 4. And then 9 pi plus 2 pi is 11 pi over 4. So now I can rewrite my thetas being subtracted as just 11 pi over 4. 4 divided by 2 out front gives me 2 times the cosine of 11 pi over 4. I don't really need parentheses again, I don't guess. Plus I times the sine of 11 pi over 4. Okay, again, you've now successfully used the formula to get it into this form, but we need to convert it to be rectangular now. So the only tricky part about this is when you use your unit circle to find these exact values, 11 pi over 4 is not on the unit circle. So what you need to do, since it's greater than the unit circle, 11 pi over 4, if you subtract 2 pi, then you will end up with a number that is on the unit circle, which is the same thing as 3 pi over 4. If you're going to use your calculator, just subtract the numbers out front. Don't put pi in there. Literally just do 11/4 minus 2, and then you'll get 3/4. And then just know that obviously you're talking about pi because we have a radians, 3/4 pi. So then in your unit circle, if you're looking at 3 pi over 4 to get these values, the cosine is the x coordinate at 11 pi over 4, which is negative square root of 2 over 2, plus I times the y value at 3 pi over 4 is positive square root of 2 over 2. And then when we distribute this 2 in, 2 over 2 will cancel to be 1, so this one will be just negative square root of 2. Plus, again, 2 over 2 is 1, so you're left with positive square root of 2 times I. So this is this final answer in rectangular form.